Well, hello there, mathletes. Welcome back. And in any case, our lecture today is going to be covering expressions and equations and kind of the relationship they have. Um, without any further ado, let's go ahead and get started here. Let's go ahead and drop that down. Now, an expression is, well, it's almost everything you see in math is an expression. An expression is numbers and variables. Um, just joined by mathematical operations. So, oh, you know what? It turns out that drawing this stuff is easier with the drawing tool. In any case, it's basically it's numbers and variables that are joined by mathematical operations, like I just said. So you know things like 2x minus 5, right? That's an expression. I have numbers, I have variables, and I'm joined by multiplication here and subtraction here. It doesn't have to be the basic four symbols. It's pretty much anything that you do a math thing to turns out to be an expression. So, you know, oh, I don't know, 5x minus 2y divided by z times, let's just throw y in there again. Here's another example of an expression. And, you know, expressions, even though it's not, I don't know, technically they are expressions even without mathematical operations, but you can have an expression that's as simple as just a number as well, or just a variable. Now, the difference between an expression and an equation is the equal sign, right? An equation is actually a sentence. It's saying that this side is equal to this side. So it's telling you a relationship between two completely separate quantities. So, you know, here's an expression. I don't know. Here's an expression. And if I put an equals between those two, what this is saying is that 4x plus 5 has the same value as 0. And so when we solve this thing, what we're doing is we're trying to find the value of x that makes this sentence a true statement. Okay, so that's what it means to solve. And I'll talk about that again when we get back to equations. You cannot solve an expression, right? You can only solve equations. Let's go ahead and clear this off here and we'll take a look at some of this stuff. There we go. Okay, so if I have an expression, in fact, this will be the one example I actually do as far as evaluating expressions. If I have an expression here, and let's say I have z times z minus 4x. Ooh, that's quite an expression, isn't it? Well, you know, if I look at this and I ask myself what the value of this expression is, I have no way of telling because there is no equal sign in this. The equal sign is what would tell us what the expression was valued at. And because of that, you really can't do much besides simplify an expression, right? Now, here's the thing though. If you happen to know what the value of the variables are, you can evaluate an expression. In fact, when you look at the word evaluate, you can see the word value in there, right? So it's to make it equal to a value. To find a value is to evaluate. But I can't tell what this thing is equal to, what number it represents, until I know what x, y, and z are. So what I would be told, I would be given an expression and told to evaluate, and then I'm going to be given certain values of the variable. So let's see, what do I have for this particular problem? Let's see, we got x is equal to negative 2, y is equal to positive 2, and z is equal to 3. Okay, so this is how I like to do things. Basically, what we're going to do is take these numbers and replace all the variables in over here with the values that I've given them, right? So you can't evaluate unless you already know the values. And so any homework problems you get for that, you'll be given the values to plug in. And we just need to decide where they go. So let's see here. I'll put them in red, I think. So let's see. I have y, and y is equal to 2. So I'm going to put a 2 down here times, and now I need x. X is equal to negative 2, right? And then the minus 3 stays the same. And then I have minus 2 times z. And so z is equal to 3. And then let's see here. In the bottom, I have z, which is 3. Oops, I wanted to do that in red. There we go. So z is equal to 3. And let's see, we got another z in here. So you replace all the z's by the value you're given. Let's see here, and that would be minus 4 times x. And so x is equal to negative 2. So this would be negative 2 here. And so this is our expression now. Oops, I need to close that last parentheses there. There we go. So this is our expression. I've replaced all the variables with the values that I've been given for those variables. And if you notice, this looks an awful lot like an order of operations problem now. And that's because it's basically what it is. Once you plug in all your variables, you're back to order of operations. And so all you got to do is just crunch this thing down. And so I'm going to go ahead and do that as we go through here. So let's see. I'm going to start with, I got parentheses in the top, and I have some stuff going on in parentheses in the bottom. So I'll do one step in each one of those. Negative 2 minus 3 is negative 5. So this is now 2 times negative 5 minus, and then because of the fact that the answer I get for this product is not going to affect the answer I got for adding negative 2 plus negative 3, I can work that out at the same time. Then down here, let's see here, I have negative 4 times 2, and that's going to, or negative 4 times negative 2, that's going to give me positive 8. So that means in the bottom, I have 3 plus 8 now. All right, so we've simplified this down a little bit. So let's keep going here. If I do one operation on the top, 2 times negative 5 is negative 10, minus 6. And then down here, 3 plus 8 is 11. So this is now 3 times 11. And then we'll go ahead down to the next line here and finish our last step for each one of these. Negative 10 minus 6 is negative 16. And 3 times 11 is 33. And these two numbers don't have any common factors. You can go ahead and search for them if you want, but you're not going to find anything other than 1 that goes into both the numerator and denominator. And so you're done right here. And so the process when you're evaluating is you're handed an expression with a bunch of variables in it, and then you're handed the values that those variables represent. So here's our expression. So our expression's here, our values are here, and all we did was take these guys and plug them in, and then used our knowledge of order of operations to go ahead and finish up the problem, right? And so that's how evaluation proceeds. It's really just replacing all the variables with the values that you're given for those variables, and then computing the order of operations that follows. All right? Okay, so let's go ahead and clear this off. Okay, now when it comes to equations, as I said before, the equal sign is what really makes the difference. So if you have something like, I did just hit that, right? Oh yeah, there it goes. Okay, if you have something like 3 times x plus 1 equals 6, right? This really is a sentence. I mean, you can write it out. 3 times x plus 1 equals, or I use a symbol. Okay, yeah, I just work here, guys. Equals 6, right? You can write, I still didn't write the word. I'm pretty ingrained here. Equals 6. There we go. That's what I was trying to do. Okay, and what we're doing is trying to find what number I can put there that will make this sentence a true statement, right? Because we don't want our statements to be lies. So you can actually, if you really wanted to, and you're like one of these crazy English grammar people, if you really want to break down, when you look at something like an equation, I'm just going to write something that we know is true, right? 5 plus 3 equals 8. That's definitely a true statement. But really, when you break this down into a sentence, the equal sign, the word equals, is your verb, right? And so 8 is your predicate, and 5 plus 3 is your subject. And actually, if you really want to get all grammar Nazi, 8 would be a predicate nominative. So it really is a sentence. There's nothing about this that is not a sentence. In fact, I'll tell you what, if you want to start a good argument in the English department, right? I did this one time. I gave them 5 plus, in fact, it was this 3 equals 8, right? I gave them this, and I said, okay, what part of speech is plus? No two of them could agree. It was great. So if you ever want to start a fight in the English department about math, that's a good way to do it. Okay, so let's actually, that was kind of an extra thing there. Now let's take a look at what we're actually going to be doing to this, or doing with this. What I want to do here is find the value of x that makes this a true statement, right? Okay, so at the onset here, you're just going to be given some values of x and you have to try them. So, maybe x equals 5 and x equals 1, and you're asked which of these are solutions. And by the way, when you're asked that question, they might both be solutions. Some equations have more than one solution, so you do need to try them all. Okay, so to check to see which one's a solution, what we do is we just plug it in. We evaluate both sides of the equation to see if we get the same number on both sides. That side is already a 6, so I don't need to evaluate that. I just need to evaluate the left-hand side. So we're going to try x equals 5, and we're going to see if that's a solution or not. So this would be 3 times 5 plus 1 equals 6. And probably you already see that this isn't true, but if we go ahead and just simplify this, 5 plus 1 is 6. 3 times 6 is not 6, it's 18. And so you notice when I plug in the wrong value, what I get at the bottom is a lie. 18 is not equal to 6, not in any way, shape, or form. So because you got a lie, that means that this possible solution is not a solution, right? It does not work because this is not a true statement. What we want is a value of x that will make it a true statement. So let's try our other possible solution. X equals 1. So let's plug it in. So that means I have 3 times 1 plus 1 equals 6. Well, 1 plus 1 is 2. So 3 times 2 is equal to 6. And we know 3 times 2 is 6. And just to finish it up, make it feel nice, we can go ahead and write our 6 equals 6. But you can stop this as soon as you see that it's going to be a true statement. And that is true, right? And if it makes it a true statement, that means this is a solution, right? X equals 1 is a solution to the equation x, or 3 times the quantity of x and x plus 1 equals 6. So really, it's just about plugging in the values they give you, see which ones work. And by the way, this is also a very good way to check your answers. So when you get an answer at the end of a problem, if it's supposed to be a solution, you should be able to plug it back into the original equation and get a true statement out of it, right? So that's what you're going for, is you're looking for a true statement. In fact, mathematics is all about the pursuit of truth. Yeah. Let's see here, we want that and that. Okay. So Let's go ahead and look at what it takes to solve an equation now. There's a button. Okay, so let's see, what do we have here? Um, Now, all of this is based on this idea of undoing operations. There are certain operations that undo each other. So, for example, if I have multiplication and I want to undo multiplication, I use division. And if I have division and I want to undo division, I use multiplication, right? And the same thing with addition and subtraction. Subtraction will undo addition, and addition will undo subtraction. So as long as you can identify which operation you have, you can use the undoing operation to peel that layer off, so to speak. And so we're going to start with one-step equations, right? Now the rules for equations are basically whatever you do to one side, you have to do to the other side as well. So if I have something like y plus 4 is equal to negative 2. If I want to do something to both sides here, or if I want to change one of the sides, I have to change the other side in the exact same way. And the rules and the goal of the game is to try to get the variable by itself, right? You want the variable on its own on one side. So in this case, we have a y. So in my last layer of computation, I want to have y equals something, right? A number. It needs to be a number. There can't be any y's on the other side. It's got to be a single y equal to something. Okay, so here we have 4 operations, and what I'd really like to do is get rid of this plus 4 so that I can get the y by itself on one side. And so I look at this, adding 4, the reverse operation, the undoing operation for adding 4 would be subtracting 4. And so I'm going to subtract 4 from both sides of this equation. Right? And if you look at this, well, right here, the y doesn't have any like terms to collect, so it's just a y by itself. And then 4 minus 4 is 0. So zeros don't really affect anything with addition. So that means that I've effectively canceled this side of this part of it out. The equal sign still needs to be in its place. And then here, negative 2 minus 4 is going to give me negative 6, right? And if we want to check our answer, what we do is we take our, we're proposing that y equals negative 6 is the solution to y plus 4 equals negative 2, right? We're proposing that's a solution. So that means I should be able to take this and plug it in for y and get a true statement. So I have negative 6 plus 4 is equal to negative 2. Now, just as a real quick review of how you add numbers with opposite signs, one of the ways I like to look at it is the number part of it, not the sign part, but the number part of it tells you how many of the signs you have. So this is, I think about it this way. This negative 6 means I have 6 negatives. And then this positive 4 means I have 4 positives. And anytime you pair a positive and a negative together, they cancel. So I've canceled these 4, and you notice what I'm left with is 2 negatives. And so my last line here is negative 2 equals negative 2, which is a true statement. And so y equals negative 6 is the correct answer, right? And so you notice the operation we used to undo addition was subtraction. If it was a subtraction there, I would use addition to undo it, right? And so addition and subtraction are undoing operations for each other. That's what you want to be thinking. I need to get rid of this 4. What's holding it on? The plus is. So that means I have to undo it with a minus. And so you want to be thinking about that as you go through these things. So, real quick here, I'm going to give you one to try. Actually, I'll give you 2 to try. So let's do our first one. a minus 4 is equal to 3. So there's our first one. And then we have x minus 1/2 is equal to negative 3/5. Okay, so we've already talked about fraction stuff and how to do operations with fractions. So this is kind of putting a couple of things together. But go ahead and pause here and see how you do. Okay, so now that you're back, let's go ahead and take a look at these two. So looking at the first one, I know I want to get a by itself on one side. It actually doesn't matter which side, as long as it's just by itself on a side. Okay, so we have it here. The only thing keeping us from getting a by itself is this minus 4. So I need to undo the minus 4. So over here, I can see if it's minus, that means I undo it with a plus. So that means I'm going to go plus 4, and that means I have to do it to the other side of the equation too. So that'll cancel, and I get a is equal to 7. And then we can check. Right, here's my check. Let's see, a minus 4 equals 3, so that means that 7 minus 4 should equal 3, and 7 minus 4 is 3, so that works. Right, we win. A equals 7 is the correct answer. Okay, now the second part might take a little bit more work just because of the fact that it's fractions, but it doesn't change any of the procedure, right? Your undoing operations are still the same. So when I look over here, I'm subtracting 1/2, right? And if I'm subtracting 1/2, the only way I'm going to be able to undo that is to add 1/2. So I'm going to put a plus 1/2 here. And I can't just do it to one side, I have to do it to the other. Now, minus 1/2 plus 1/2, since they're opposite signs of the same thing, is going to cancel out. And so I should just get an x equals here. But I need to do this addition. Now, this is one of those cases where the addition is a little more than what you can do in your head. Like over here in the previous example, over here, this addition and subtraction we could do in our heads. Fractions, probably not. If you can, oh, God bless you. You're pretty good at stuff. But I think probably the majority of people can't. So let's write down what I'm actually trying to figure out here. I need negative 3 over 5 plus 1/2. So that means I'm going to need a common denominator. Now between 5 and 2, that common denominator is going to be a 10. I know this one is negative, and I know I'm adding them, so now I just need to find the new numerators. So to make a 5 a 10, I had to multiply by 2, so that means I'm going to multiply by 2 here also. And negative 3 times 2 is now negative 6. And then over here, to make this 2 into a 10, I had to multiply by 5. So 2 times 5 gives me the 10. 1 times 5 gives me 5. And if I add them together, I get, let's see, negative 6 plus 5. So there's only 5 positives to cancel out 6 negatives. That means I'm going to have 1 negative left over and a denominator of 10. So we're supposing now that this is equal to negative 1/10. Now, I'm going to need to make some room. We have to check our answer real quick. It's always a little tougher to check fractions just because they require a little bit more work to do the arithmetic. But it really is a good exercise. So let's see what we got here. So we say x minus 1/2 is negative 3/5. So let's put in negative 1/10 and see if it works. So it should be negative 1/10 minus 1/2 equals negative 3/5. So that means we have to operate on this side and see if we can reduce that down to negative 3/5. So my common denominator is going to be 10. So I have negative 1/10 here. And to make that one a 10th, I'm going to multiply by 5. Let's see here. Yeah, so let's see here. Let's say that gives me 5/10. So negative 1 minus 5 gives me negative 6/10. And if I reduce that fraction by 2, I get negative 3/10, or 3/5, excuse me. I just work here, guys. Let's try this again. Okay, so I get, there we go. I get, I'm trying. Okay. I get negative 3/5, and that matches what I have over here on this side. So what we end up with is negative 3/5 equals negative 3/5. We win, right? Negative 1/10 is the correct answer. Okay, so let's go ahead and clear this off now. Okay, so let's see. Let's put this back up. We know that plus and minus go together, that multiplication and division go together. Those guys undo each other. Okay, so at its most basic form here, if I have something like, oh, I don't know, 3x is equal to 81, and I want to solve this. Now, there's nothing added or subtracted in here. The only thing keeping x from being by itself is this 3. And this 3 is attached by multiplication. Well, if I look over here, I can see that multiplication is undone by division. And so what I'm going to end up doing is dividing both sides by 3. 3 divided by 3 is a 1. So this is now 1x. Right? We don't need to write the 1. The 1 is understood when you just write x by itself. And then over here, we have to divide 81 by 3. Now, it is 27, but if you actually want to go through the division, let's see, 3 goes into 8 twice. Let's see here. Let's see, that makes 21, and 3 goes into 21 7 times, and that leaves me with a 0 remainder. So I come out with 27. And, when I'm checking this, that means that 3 times 27 has to be 81, right? Because you can always rewrite a division as a multiplication, or multiplication as a division, or what have you. Here, we just want to check. Basically, if 81 divided by 3 is 27, then 27 times 3 should be 81. And we can check that real quick, too. Right? 3 times 7 is 21. 3, now this 2 represents a 20, so we'll have to put that down. 3 times 2 is 6, and if I add those together, I get 81. Right? Interesting, too. Do you notice I have a 6 here and a 21 here? They have a lot of the same numbers pop up. So yeah, 81 is equal to 81, and so this works, right? We have a little check mark there. Okay, so that's our quick example. Now I want to give you guys something to play with. So let's do that and this. And so I'm going to give you, let's do 3 examples this time. So we'll look at each one of these separately. And let's see. Doggone it. Try this again. And let's see what we can do with them. I'm going to box that out of the way. Okay, so let's start with the first one. Let's say 5 times a is equal to, let's say 80. So that's your first problem. And then x divided by 5 is equal to 2. So there's your second one. And then the third one is going to be 2/3 times x is equal to 5/2. Okay, so there's 3 problems here, and they kind of move up in difficulty as you move across. So go ahead, pause here, and see if you can do these on your own first, and then play it again. Start playing again once you reach a point where you're either stuck or satisfied you have an answer. Excuse me. Okay, so you're with me here. Let's go ahead and take a look at the answers to these things. Now again, 5 is multiplied by a, so to undo it, I have to divide by 5. So we'll divide that 5 off. 5 divided by 5 is 1, so that gives me an a. And now I just need to see how many times 5 goes into 80. So let's see here. I'll just do the division down here. So 5 into 80. Ooh, that's a bad spot for it. I'll just put it here. Five into 80. So 5 goes into 8 once. That leaves me 3. So 5 goes into 36 times. And so I get 16. So A is equal to 16. And I'm going to skip the check on this, but you can check it by doing 5 times 16 and seeing that you get 80 out of it. Okay. Now, over here, here's what's kind of interesting is that with this one, the 5 is attached by division now. And so that's something new. So how do you undo division? That's a good question. Well, let's look over here. Turns out you undo division with multiplication. It works both ways. So that means I'm going to, if I want to undo this division of 5, I need to multiply it by 5. And if I do it to one side, I have to do it to both sides. Right? Now here, whenever you multiply by a whole number, if you need it, you can always put it over 1 to remind yourself that it is still a fraction. And so you can cross cancel here. Right? And so that's basically turns into a 5 divided by 5, which ends up being a 1. So I have x. And then over here, 2 times 5 is 10. And you can check that. In fact, you could probably do it in your head. If you just put the 10 in here, 10 divided by 5 is 2. Right? So we have that answer. Okay. Now, I want to do this here. Let's go ahead and erase some of these things. And this I'm going to move. That didn't work. Come on, where's the moving thing? Looks like I can't grab it. I was going to move it over. Okay. Well, live and learn. We'll leave it where it is. So we have, I'm just going to rewrite it because that'll make it easier. Can't pull it off with this technology. Okay, let's try it one more time here with the writing tool. So 2/3 x is equal to 5/2. Now, there's more than one way to actually do this one. So first of all, one of the things that you can do when you're multiplying by a fraction, remember that whenever you divide, you would be dividing this particular fraction off, right? We'd be dividing by 2/3, but if I divide by a fraction, I'm going to flip it and multiply anyways. So you can actually do that on the first step, right? So by multiplying by its reciprocal, that's the same thing as dividing. So that means I have to do it on this side too. So here, that will cancel with that cancels with that, and that leaves me with a 1. So I just have x by itself here. And then on this side, I just need to multiply everybody out. 5 times 3 is 15, and 2 times 2 is 4. And so, this is actually not a bad thing to check. I know it seems like it should be harder to check fractions, but you're just multiplying them. And that's something that actually goes pretty quick. So the original equation was 2/3 x. We're saying x is now 15/4. And we're saying that should be equal to 5/2. Right? That's what we're looking at. So let's see if we can simplify this and see if we get 5/2. So the 2 cancels with the 4 to leave me a 2. 3 cancels with 15 to leave me a 5. And if I multiply this back, I get 5/2. That is... You can tell I've been doing these videos for a while today. Okay, so 5/2 equals 5/2. And so that works, right? We have our check. And that's probably the quickest way to get a hold of it. Now, the other thing you can do is to break that fraction into 2 steps, because that fraction means 2 things. That means x is being because it's 2/3, x is being multiplied by 2 and divided by 3 at the same time. So you could break that into 2 steps if you really wanted to. So let's look at doing that. So this is just an option. This isn't how you have to do it. I actually think this way is probably the quickest, but this way breaks it down into more bite-sized steps. So since this is a multiplication by the numerator and a division by the denominator, one of the things I can do is just take those two things as separate operations. So I'm dividing by 3. So it actually might be nice to take both sides and multiply by 3. Right? And if I do that, remembering that's 3 over 1 here, because I just need to remember it's a fraction, 3's will cancel, and I end up with 2x, and let's see, nothing cancels over here, is equal to 15/2. Right? So that's one step. You don't have to keep track of quite as much. Now what you would do is divide both sides by 2. In fact, let me just do that in a different color just because. And remember again, that's 2 over 1. So this cancels, and I actually get x is equal to, well, we're dividing by a fraction, so we're going to flip and multiply. So it's 15/2 times 1/2, which gives me 15/4 again. Right? So there's 2 different ways to do that one. There's actually more than 2 different ways to do it, but those are probably the most straightforward 2 ways to get a hold of it. Okay, so that actually rounds out all of the material that we need to cover for today. Let's see here, what am I, oh, there it is. There we go. So this has been absolutely wonderful and fun, and yeah, you guys can look forward to the next part of the lecture, or I should say the next lecture. Yeah, sometime this week. Anyways, until next time, keep your pencil sharp, and yeah, see you later, guys.